First of all, thank you to the organizers for giving me the opportunity to present a talk over here. It's a pleasure to speak in Cosmology from Home 2024. Now, as you can see that I'm going to speak about something which is a very sort of exotic name, but let me just give you a brief idea that the idea is to probe new physics or to look up for new physics with the help of gravity, or more precisely the gravitational wave, or how we can produce new physics with the help of gravity mediation. So this talk will be based on a couple of the work which are shown over here that I have done in the last few years. So without wasting much time, let us begin. I will start with a very small sort of introduction about the uncharted territory beyond the standard model, that where the standard model fails and what are some aspects that we need in order to understand the beyond the standard model physics. For example, the dark matter or matter-antimatter asymmetry, etc. I will basically focus on these two things. Now, as we know that this is the standard model of particle physics as it stands now. After the discovery of the Higgs boson, the full picture is complete. And of course, standard model has been tested over and over in different experiments over decades and have been found to be an excellent explanation of the nature. But in spite of its robustness and accuracy, there are some windows which are still open where the standard model of particle physics fails. And therefore, we need to seek some physics beyond the standard model. One such instance is, of course, the light neutrino mass. We know that the light neutrinos within the standard model are practically massless because of the very structure of the standard model itself. So in order to explain the mass of the neutrinos that the oscillation experiments have shown us, we need to add some more fields, or we need to add some more physics on top of the known physics of the standard model, and that's where the new physics comes in. And secondly, of course, the matter-antimatter asymmetry, which tells us that why there is more matter than antimatter in the universe. All the stars and the planets that we see around us, these are basically made up of baryons or electrons and not antibaryons or positrons. And therefore, the natural question is, what is the mechanism that made more matter than the antimatter? And finally, is this pie chart over here, which comes from the measurement of the cosmic microwave background. And this tells us exactly only 4% of the universe is visible to us, while around 72% is completely unknown, which is called dark energy, which I'm not going to speak about, of course. Rather, I will concentrate on this small 24% of green region, which consists of something called dark matter. And I will try to motivate that how these dark matter particles were produced in the early universe with the help of gravity. Now, before I really jump into the main theme, let me first try to convince you that we actually have seen dark matter. There are plethora of experimental evidences of dark matter in the universe. And I have just listed two such evidences, One being the galaxy rotation curve, which perhaps is one of the oldest evidences of dark matter, which tells that as we move from the central bulge, or the most luminous part of the galaxy, and go towards the outskirts, then I expect that the radial velocity of the stars in the galaxy should decrease following the Keplerian law. However, it starts increasing and then becomes constant. And therefore, there is an apparent discrepancy between the two, which tells that there is something which is lurking somewhere over here, which is non-luminous and perhaps non-baryonic, and it's influencing the motion of the stars in the galaxy. And that's perhaps what is known as dark matter today. The second evidence comes from the cosmic microwave background radiation, which is practically the afterglow of BBN. And these are the photons that are coming to us from the end of Big Bang. And we can measure the tiny amount of temperature and anisotropy of this microwave background. And from that, we can infer that what amount of dark matter is present in the universe. Now, from these evidences, of course, we are certain about some facts. Of course, we do not know exactly what sort of entity dark matter is, or what is this particle nature, or if at all it's a particle to begin with. But we are certain about some of its properties. For example, it does not talk to photon, and that's why it's non-luminous. but it certainly gets influenced by gravity. That's why it influences the motion of the stars, and it's stable on the scale of cosmological lifetime. Now, when we go back to our known catalog of standard model of particle physics, in order to understand the particle nature of dark matter, we see that these properties are actually being satisfied by the light neutrinos. However, the neutrinos within the standard model are too light to become dark matter candidate, because they cannot make up all of the 24% of matter energy budget. And therefore, in order to explain a viable cold dark matter, we need some new physics on top of the standard model. And the second one is the matter-antimatter asymmetry. The idea is that after the Big Bang, perhaps matter and antimatter were produced in equal amount, or perhaps there was an asymmetry to begin with. But in any case, there was a period of fast expansion called inflation that totally erased all the initial asymmetry. And therefore, the matter-antimatter asymmetry that we see today perhaps have been generated dynamically after the inflation. Now, again, we do not know that what exactly is the underlying mechanism that generated more matter than the antimatter, but we are certain about that it needs some ingredients or some conditions. For example, it has to baryon number violated, it has to violate C and Cp, and also it needs an out of equilibrium condition, which are together known as Sakharov conditions. In any case, again, the standard model of particle physics has all the ingredients that can produce the matter-antimatter asymmetry, but not just in enough amount, which means that we cannot explain the observed matter-antimatter asymmetry that experiments show us. And again, therefore, in order to explain the observed asymmetry, we need to have some more physics on top of the standard model. So this talk will be majorly dedicated on these two mysteries that sort of cosmology or astroparticle physics offers to us. Now, as I was telling, that this talk is going to be around two numbers practically. One being the dark matter relic abundance, which is around 0.1. Another is the baryon asymmetry, which is scaled, and it's reported as 10 to the minus 11 or so. Now, these numbers can be explained with the help of several theories, right? We can make up many particle physics models, which can address questions like what sort of particle dark matter can be, what can be its intrinsic spin, how it interacts with the physical universe with us, or if we can have a common origin of both dark matter and baryon asymmetry, so that we can get a sort of a unified model. And most crucially, that how the production of these relics were influenced by the gravity or the background cosmology in the early universe. And of course, the most important point is that whatever the theory is, how elegant it looks like, it should have an experimental evidence. That means we should test the theory against the existing experimental data. And data, for example, can come from collider experiments like the Large Hadron Collider, astrophysical experiments, for example, the LIGO, which have detected gravitational wave recently, or it can come from experiments that measure cosmological observables, for example, CMB. India itself has its own CMB mission, which is going to get launched at some point of time, which is called CMB Bharat. So the idea is to make not just to make a model, but also make the model testable, so that we can have some predictions, or we can have some bounds or constraints on the corresponding model. Now let us go into the core of the topic. That now we have set the stage. Now we have shown our cards that what are the things that we are going to talk about. Here we will, from here onward, we will discuss about that how we can probe new physics with several gravitational signatures, perhaps through a gravity portal, through primordial gravitational wave detection, or through non-minimal coupling with the gravity. So let me start with the first one, which is the gravity portal. The idea is as follows: that in order to explain all the dark matter abundance or matter-antimatter asymmetry, as I was telling you, that we need some new physics. And here we extend the standard model with some new physics fields, and these fields are practically singlet under the standard model. For example, this can be singlet fermions, or this can be singlet scalar. Now, the singlet fermions can be dark matter candidate if they're completely stable, or they can undergo decay in a Cp violating manner and can produce the matter-antimatter asymmetry, which is of course known as the leptogenesis. On top of that, once you add some singlet fermions, inevitably you can also produce a tiny neutrino mass, what is known as fire-type consistent. The singlet scalar, on the other hand, can play the role of an inflaton, which caused inflation in the very early universe. And at the end of inflation, during the time of reheating, it produces all the standard model path. And the crucial factor here is the fact that all of these are produced only simply via gravity portal. And this gravity portal can appear minimally, which is inevitable, which is suppressed by this Planck scale, or it can appear non-minimally through a coupling like this. But here the crucial thing is that the background equation of state due to this particular form of inflaton potential can be stiffer with respect to the radiation, which means that the energy density of this field, which is the inflaton field, can decrease faster than the radiation. Now, it has an advantage. The stiff background has an advantage. It improves the possibility of the model being detected at gravitational wave detector. Let me explain how. So the idea is that the primordial gravitational waves that are produced during inflation, they first leave the horizon because during the inflation, because the Hubble horizon is decreasing with time. And at some point of time, when the inflation gets over, then all these perturbations starts entering the horizon, and they form the gravitational wave background, which is a stochastic gravitational wave, which is always present. Now, if this happens during the period of the stiff period of time, then all the gravitational waves gets a boost, and they become heavily blue tilted, as you can see the figure over here. And this blue tilt actually helps the gravitational wave to be detected with several gravitational wave detectors, for example, BBO, DESIGO, LISA, etc. So this stiff period of time practically boosts the amplitude of the gravitational wave and therefore improves their visibility in several detectors. But everything comes at a price. The price of improvement in sensitivity is being paid by the BBN. You cannot produce excessive amount of any new radiation on top of the standard model around the time of BBN, because in that case, you will hamper the production of known light particles, which are produced during this nucleosynthesis. And that's why you have this blue band over here, which is excluded by BBN for production of excessive gravitational waves during that period of time. So this actually not only helps us to probe the model, but also helps us to constrain the model. For example, here in the left panel, all these black curves over here, these correspond to right amount of relative density for the dark matter. The dark matter being a fermion in this case, and you see the dark matter has to be very massive in order to overcome the suppression due to Planck. And now all these green curves over here, these are practically sensitivity from different gravitational wave experiments, and you see that these are showing that all the viable parameter space can be probed with these kind of experiments. Not only that, there is a blue band over here which tells excessive gravitational wave, below which you cannot go, because then you will be in conflict with the BBN. And therefore, it also tells you that how massive the dark matter really has to be in order to be viable from BBN bound. The same also is applicable to the viable parameter space that produces the observed matter-antimatter asymmetry. Here again, we see different curves correspond to the observed and asymmetry. And again, you cannot go beyond this blue band because you will be in problem for missing of the BPN. And therefore, we cannot have a mass below 3 times 10 to the 11 GeV that can decay in a superviolating way and can produce the observed matter-antimatter asymmetry. So the statement here is that the primordial gravitational wave, the gravitational wave that is coming from inflation and being blue tilted because of this stiff period of time can help us both probing and constraining the corresponding viable parameter space that can simultaneously produce or simultaneously explain dark matter and baryon asymmetry. And not only that, we can have non-gravitational coupling between the inflaton and the standard model particle, because we have no idea that how exactly this reheating occurred. And therefore, one can propose that there can be different couplings between the singlet scalar that drove the inflation, this phi, and the standard model particles. For example, this can be a pair of fermion, a pair of vector boson, or a pair of scalar. And now, thanks to the presence of the primordial gravitational wave and its blue tilted nature, we can actually put some bound on this coupling over here. This is shown in this plot. You can see that this different curve over here correspond to different coupling between the inflaton and the pair of scalar in the standard model, for example, the Higgs. And you cannot go below 10 to the minus 15. Then again, it will be in contradiction with the BBN prediction, which does not allow more gravitational wave over the existing radiation from the standard model path. And the coupling over here is very, very tiny. And such small coupling are practically beyond the reach of collider experiments like LHC, because they typically look for very large coupling. And only such small coupling can be either constrained or probed with the help of gravitational wave or primordial gravitational wave in this case. On top of that, one can also have more new physics. For example, one can think of axions, right? Axions are very well motivated candidate, both from the perspective of particle physics, which solves the Stokes-Levy problem, and from the perspective of cosmology, that can be a viable dark matter candidate. And in reality, axions are being looked in several different experiments, for example, coming from astrophysics or cosmology, or from different laboratory-based experiments. And they are typically looked up through this coupling with the photons, this AFF tilde coupling. And people have projected bounds on this GA gamma, which is the coupling strength between the axion and the pair of photons. Here we see that how the primordial gravitational wave can act as a complementarity to existing axion experiments, which typically look for this photon signal. And these experiments practically are the cavity resonators. And over here, I show you the complementarity between cavity resonators and gravitational wave probe. The red band over here is practically excluded by the BBN bounded gravitational wave. Again, same as before, while the blue band is the allowed one. And therefore, it tells you that if we produce the axions during reheating, then practically we can have a complementarity between axion-based experiments and the gravitational wave probe. And since I'm running out of time, I will tell you that, well, on top of such searches, we can also test inflation, for example, at the ice cube, where you can actually test very high energy neutrino flux thanks to the decay of very massive neutrinos. And moreover, we can also have decay of the inflaton into a very highly energetic gravitational wave, which is basically gravitational Bremsstrahlung. And it's a unique signature because it tells you that the gravitational wave frequency is very, very high. And finally, you can also have some probe or a model where you can have a very simple scenario where inflaton decays via this non-minimal coupling